So this is lecture 12 on linear transformations. So we are in chapter 4, and this is section 4.4. So we've been introduced to vector spaces, not just Rn, but an abstract vector space V. The most important examples are Rn and Cn, but they're not the only examples. And we have the notions of linear combination, linear dependence, linear independence, basis, and dimension. So these are discussed in sections 4.1, 4.2, and 4.3, and we've already talked about them and have some homework problems on them. If this is your first exposure to so-called abstract mathematics, this can be, it can take a while to understand it. It takes a lot of time to study. And you have to study the book very intensely. So let's just recall a set S of vectors in V generates the subspace W if every vector in W is a linear combination of vectors in S, and if every linear combination of vectors in S is a vector in W. So we say W is generated by S, and often we write S in brackets to indicate this. Means W is the set of all vectors of the form summation xi vi. I goes from 1 up to k, where v1 up to vk are vectors in S, and x1 up to x of k are scalars, say real numbers. The set V is a basis for the subspace W if V generates W and V is a linearly independent set of vectors. And what is sometimes called the fundamental theorem of linear algebra says the following. If B1 and B2 are two different bases for the subspace W, then B1 and B2 contain exactly the same number of vectors. So all bases for a subspace of a vector space have the same number of vectors, and this number is called the dimension of W. So the dimension of the subspace is the number of vectors in a basis. Now, this is really extremely important. This was discussed in section 4.3. Now we want to consider functions from one vector space to another, so that V and W be vector spaces. A function T from V to W is called a linear transformation. If it satisfies the following two properties. For all vectors V and V prime in V, T applied to the sum of those two vectors is T of V plus T of V prime. This is a vector in W. So if I take two vectors V and V prime in V, if I add them in V and then take T of that vector, I get exactly the same thing as if I take T of V and T of V prime, and I add them in W. And the second property says, for all vectors V and V, and all scalars C in R, T of C times V is CT of V. So this is the definition of a linear transformation. You must know this. You must know it by heart. If you don't know the definition of a linear transformation, you won't be able to solve any problem in linear algebra from here on in to the end. And remember, even though the final exam is a week from today, by the summer school schedule, it's almost like we have another month of classes over the next 3 or 4 days. Every day is a week of work. So what are some examples? Suppose V and V prime, so suppose V and W are R2. So a vector V is of the form, let's say, x1, x2. And define T of V, or T of the vector x1, x2, would just be the vector x1, 0. So if you want a picture of what this looks like, if this is R2, if this is the vector x1, x2, this is the vector x1, 0, and our linear transformation takes this vector and just projects it onto the x-axis. So geometrically, that's what this function does. And I claim this is a linear transformation. So suppose we have V is x1, x2, and V prime is x1 prime, x2 prime. So V plus V prime, if I add the two vectors, is x1 plus x prime, x1 prime, x2 plus x2 prime. So T of V plus V prime is T of the vector x1 plus x1 prime, x2 plus x2 prime. That's T of, projects it onto the first coordinate, that's x1 plus x1 prime, 0. So this function T sends a vector to its first coordinate and then 0 for the second coordinate, which is the same as x1, 0 plus x2, 0, which is the same as T of x1, x2 plus T of, this should be a prime, x1 prime, x2 prime, which is T of V plus T of V prime. So that's a proof that this first condition of a linear transformation is satisfied. Similarly, if I take t of c times v, that's t of c times the vector x1, x2. That's t of the vector cx1, cx2. That gets sent to cx1, 0, which is c times x1, 0, which is c times t of x1, x2, which is c t of v. So the second condition of a linear transformation is satisfied. So this is a nice example, a simple example of a linear transformation. What's another example of a linear transformation? Here's one which is very interesting. Suppose I take a matrix A, which is A, B, C, D, a 2 by 2 matrix. And I define a function t from R2 to R2. Let me use x and y for the coordinates as follows. T of xy is going to be the matrix A times xy. That's A, B, C, D, xy. This is by matrix multiplication, ax plus by, cx plus dy, which is a vector in R2. So t of the vector xy gets sent to this vector in R2. I claim this is a linear transformation. So suppose I have the vector v, which is xy, and the vector v prime, which is x prime, y prime. So v plus v prime is x plus x prime, y plus y prime. So what is t of v plus v prime? It's the matrix A, B, C, D times this vector, which is x plus x prime, y plus y prime. I do my matrix multiplication. This is A times x plus x prime plus B, y plus y prime, C x plus x prime plus D, y plus y prime. I can write this is just a vector. This is not a matrix anymore. This is just a vector. But I can write this as a sum of two vectors. That's ax plus by, cx plus dy, plus ax prime plus by prime, cx prime plus dy prime. But this is exactly t of xy, and this is exactly t of x prime, y prime. So that's t of v plus t of v prime. So the first requirement for a linear transformation is satisfied. And it's also straightforward to check that if I take any lambda, a real number, t of lambda times v is lambda t of v. This is also satisfied. So every matrix, every 2 by 2 matrix defines a linear transformation from R2 to R2. Let's work out some properties of linear transformations. So suppose I have a linear transformation from a vector v to w. And suppose 0, so I write 0 sub v, is the 0 vector in v, and 0 sub w is the 0 vector in w. So I claim that t of 0 sub v is 0 sub w. So if you like a picture of this, if this is v and this is w, here's the 0 vector in v, here's the 0 vector in w, and t sends 0 to 0. T of 0 is equal to 0. And let's see, I can give a proof of this, which is a little sneaky, but it's okay. So one proof would say 0 plus 0 is 0. So t of the 0 vector is t of 0v plus 0v, if these are equal. And because this is a linear transformation, this is t of 0v plus t of 0v. This is a vector in W. In a vector space, every vector has an inverse. So if I subtract t of 0v from this equation, I get t of 0v minus t of 0v is t of 0v plus t of 0v minus t of 0v. But over here, if I take a vector and I subtract it from itself, I get the 0 vector. So this is t of 0v plus the 0 vector, which is t of 0v. So that is a proof that a linear transformation sends 0 to 0. And it's also true that if I take t of the vector minus v, this is always minus t of v. These are basic properties of linear transformations. Now, associated with every linear transformation, there's some subspaces. And a hint of one of them comes from the fact that t of 0 is 0. So again, I'll draw a picture. Here's v, here's w, and there's this function from t to w. If I take the 0 here, that gets mapped to the 0 over here under this linear transformation t. But it might be there are lots of different vectors that get mapped to 0. So what is called the kernel of t, it's all vectors in v, such that t of v is 0. It's everything that gets mapped to 0. So we just proved that the 0 vector in v is in the kernel of t. And there's a nice simple lemma that says kernel of t is a subspace of v. If you look at all the vectors that get mapped to 0, that's a subspace of v. And the proof follows immediately from the properties, the definition of a linear transformation, that K be the kernel of this linear transformation T, with all vectors in V, such that T of V is 0 over in W. So if V1 and V2 are in K, then T of V1 equals 0, and T of V2 equals 0. But then T of V1 plus V2, because this is a linear transformation, this is T of V1 plus T of V2. This is 0 plus 0, which is 0, which means V1 plus V2 is in the kernel. So this kernel K is closed under vector addition. And if V is in the kernel and lambda is a scalar, then T of lambda V is lambda T of V, because this is a linear transformation. But T of V is 0, and any number times the 0 vector is the 0 vector. So lambda V is in K. So this kernel is closed under vector addition and scalar multiplication. So K is a subspace of V. There are many subspaces associated with a linear transformation. Let me describe another. Again, we have T from V to W. Well, here's V, here's W, and here's T. Now, every vector v gets sent to some vector t of v in W. And so over in W, you have the set of all things of the form t of v for some v back in this vector space. So what is called the image of t, it's all vectors in W such that W is t of v for some v in v. And another lemma says that the image of T is a subspace of W. And the proof goes as follows, that W1 and W2 being in the image of T. That means that there exist vectors v1 and v2 in V such that W1 is T of V1 and W2 is T of V2. But then W1 plus W2 is T of V1 plus T of V2. But this is T of V1 plus V2. This is some vector in V. So this is in the image of T. So T is closed under vector addition. If W is in the image of T and lambda is a scalar, a real number, then T of lambda W, so then W equals T of V for some V in the vector space V, and lambda W is lambda T of V, but that's T of lambda V because T is a linear transformation. So this is also in the image of T. So the image of T is closed under vector addition and scalar multiplication. So it's a subspace. So I'm not going to prove this now, but I'm just going to draw a picture to show this. So here's V and here's W. And there's a linear transformation from T to W. So over here, we have a subspace, which is the kernel of T. And over here, we have a subspace, which is the image of T. Now, every subspace has a dimension. So what is called the nullity of T is the dimension of the kernel of T. And what is called the rank of T is the dimension in W of the subspace image of T. And the second fundamental theorem in linear algebra for us, the first fundamental theorem says that every vector space and every subspace has a well-defined dimension. This theorem says that if the dimension of V, whatever it is, the dimension of the original subspace V is equal to the sum, dim stands for dimension, DIM equals dimension. So the dimension of V equals the dimension of the kernel of T plus the dimension of the image of T, or in other words, the dimension of V is the rank, is the nullity of T plus the rank of T. So this is really super important theorem. And you're not asked to prove this in the exercises, but you are asked to apply it to work out the dimensions of the various subspaces connected with the linear transformation. Okay, so that's enough for right now. This is, and it's actually enough for Saturday, Sunday. That's it.